Okay, so hi. In this reaction, I'm going to do an sn1 example. So sn1 means substitution nucleophilic reaction, and it's 1 because it's first order, and we'll go over that later. So stick with me. Pay super close attention to stereocenters and stability as we go. And I also, side note, apologize in advance because my cat has a zoomies right now, so if you hear thumping in the background, that's him. Anyways, so the first part of an SN1 reaction is one of the lone pairs from the oxygen grabs onto the hydrogen from our HCl, and as a result, this HCl bond breaks. So we have a chlorine now that's floating around in our solution. We redraw our molecule, and now our oxygen is bonded to two hydrogens, and it only has one lone pair. Since it only has one lone pair now, that means that now it has a positive charge because formal charge is valence electrons minus bonds minus lone pair electrons. So this oxygen has 3 bonds and then 2 electrons attached to it. So 6 minus 5 is 1. That's why this oxygen is positively charged. So after this step, this part right here is the rate limiting step because this is the part where we form the carbocation. These electrons in this bond to the oxygen are given back to the oxygen so that now this whole chunk breaks off and now we have water in our solution. Our chlorine is still there, it's hanging out, we're not going to use it yet, and now we have to draw our carbocation. So this part stays the same. And when we draw our carbocation, we have to make sure that we represent it as planar. We know that there's a hydrogen on this carbon because over here, even though it's not drawn, since the OH that's stuck off is drawn as a wedge, that means that the hydrogen that's hiding that we didn't draw is actually a dash. So now that we draw a carbocation, we have to make sure that it's drawn as planar because otherwise it's not really represented as a true carbocation. And these carbocations are sp2, and sp2 carbons have 3 substituents. So our carbocation has this methyl substituent on the right side, and then a hydrogen that's drawn down, and then the other carbons that are part of the rest of the molecule. So this carbocation is secondary because it has 2 non-hydrogen substituents and a hydrogen substituent. And we also know that tertiary carbocations are more stable than secondary carbocations. So now at this part of the reaction, we have to say, okay, can I make my secondary carbocation turn into a tertiary carbocation by moving some stuff around? And the answer is yes. So there's 2 different ways that we can do this because there's 2 different things that we can move. We can only move stuff that is 1 carbon off of 1 carbon away from the carbocation. So that means that we could move the hydrogens connected to this methyl group. We could move these electrons or these electrons. And that's because they're 1 carbon off of 1 carbon away from the carbocation right here. And we wouldn't move, sorry, I'm using a different color. We wouldn't move any of these hydrogens because if we did, then we would end up with a primary carbocation, which would make our molecule less stable. And God really doesn't like primary carbocations, so we're not going to do that. It would be way more stable to move either this methyl group or this ethyl group because then we would end up with a tertiary carbocation. And we can move either one of them. There's no real preference for moving methyl groups versus ethyl groups because the main goal is just to get to a tertiary carbocation. So I'm going to draw both different kinds of carbocations that are tertiary. This M means that I'm moving the methyl group as my shift, and this E means that I'm moving the ethyl group for my shift. So we're going to do the methyl one first. And these electrons right here are leaning towards the carbocation in order to make it more stable before it actually shifts. It's kind of like leaning towards them because the positive charge really wants electrons. This carbocation is so unhappy because it doesn't have 4 substituents, it only has 3, which is why carbocations are super unstable. So moving the methyl group, we have to draw our new carbocation. This is the methyl group that moved right here. This is a methyl group that moved, and we know that there's still a hydrogen here. You don't have to draw it, but it's still there. And now our ethyl group is actually going to be still there from the carbocation. When you move something, like we move this methyl group onto the carbocation, now the carbocation is where we moved the methyl group from because we took a substituent off of this carbon and we put it onto this carbon. So now this carbon only has 3 substituents, and that's right here, that's shown right here, because now this carbon has an ethyl group and it has the other 2 parts of the molecule. So we're going to do this molecule first, and then we're going to do the ethyl shift after, because this one's like the easier part. So we know that we have chlorine and water floating around in our solution, and now our chlorine is going to jump onto the carbocation in order to form a carbon-chlorine bond, and this is how our carbocation is happy at the end. So when we form our new bond, we have a chlorine, and then this is our ethyl group. And the reason why I'm not drawing wedges or dashes on this carbon is because this carbon is not a stereocenter. A stereocenter is a carbon with 4 different substituents, and these 2 chunks of the molecule are the exact same. So that means that the blue carbon is not a stereocenter. So this is one of the products, and we know that this is a good product because it came from a tertiary carbocation. So this is a super stable product. Everything's happy, everything's great. So now we're going to do the other option of a tertiary carbocation, where we move the ethyl group instead of the methyl group. So I'm going to redraw my carbocation, and I am going to, I know that there's a hydrogen here, and here's my ethyl group that I moved, which means that I have a methyl group left over here. So I'm going to put some colors in. This is the ethyl group that we moved, and this is the methyl group that stayed. So the first thing that you should notice is that when I moved my ethyl group here, now this blue carbon is a stereocenter. So that means that when my new carbocation molecule forms, the blue carbon right here could either have the ethyl jump on as a wedge or a dash. So there's actually 2 versions of this carbocation that can exist. So I'm going to redraw this showing that. Here the ethyl group is a wedge. My hydrogen is going to be a dash. My carbocation looks the exact same. And here my ethyl group is going to be a wedge, and my ethyl group is going to be a dash, and my hydrogen is going to be a wedge. And my carbocation stays the same. And the reason why this difference exists compared to the first carbocation that we formed is that this is not a stereocenter, and this is a stereocenter. So we have to show that we know that, because that changes how our products look at the end. So now that we have these 2 different carbocations, I'm going to move them. I'm just going to copy and paste them so that we have some more space. I'm going to put them right here. These are the exact same molecules that we used. So now, just like how we did with the first carbocation, now our chlorine is ready to jump onto the tertiary carbocation and form a happy molecule. So since we started with a stereocenter, we can have at least 2 different products where our chlorine jumps on to the carbocation, where the other stereocenter is a wedge for the ethyl group, or where the other stereocenter is a dash for the ethyl group. But when we add our chlorine in here, I'm going to use a different color. When we add our chlorine into here, now this new happy carbon that has 4 bonds is going to have a stereocenter, because if I redraw it without showing wedges or dashes, here and then like this. So that means that now this carbon that used to be a carbocation will also have a stereocenter. So that means that when the chlorine jumps onto the carbocation, it could also form as a wedge or a dash. So as a result, that means that instead of having this product that we already talked about, this product, and then 2 more products, now we're actually going to have 2 more on top of the 3 that we have, that we knew that we were going to form, because there's 2 stereocenters in this molecule. So it looks really funky, but just work with me. So I'm going to erase this, since we know that it's not the most accurate way to represent our product, but we do know that chlorine is going to come in on the carbocation regardless. So our products are going to be 2 products from the one where the ethyl group is a wedge, which is right here from this molecule, and there's going to be 2 products from where the ethyl group is a dash, because when the chlorine jumps on, it forms a new stereocenter. So this is me just drawing the products. So what stays the same from this chunk is that both of the molecules that we draw are going to have the ethyl group as a wedge. So I'm going to draw that first. And now when we add our chlorine could either form as a wedge or it could form as a dash, which means that our methyl group would just be the opposite. So these are the two products for this molecule. And I'm going to draw the other two products for the other molecule. So what stays the same between these two is that the ethyl group stays as a dash. This chunk stays the same, but my chlorine could form again as a wedge or as a dash, like that. The reason why we had to do so much extra work is because of stereocenters, and stereocenters are super important, so make sure that you pay close attention to those. But I'm going to run through it one more time so that we see everything going on. I'm going to use my little pointer and we're going to talk about it. So, first thing, happens in every SN1 reaction, this oxygen is going to grab onto a hydrogen, and now this oxygen has two hydrogens attached to it. And the chlorine jumps off, it's in our solution, we don't care about it right now. Then, the lone pairs in this carbon-oxygen bond are given back to the oxygen, so this whole chunk falls off, and now we have water in our solution along with this chlorine ion. And then we form our carbocation. We decided to do a shift because our carbocation is secondary and tertiary carbocations are infinitely more stable. And in this problem, we have the option to move either a methyl group or an ethyl group. So we did that both ways. This one's with the methyl group shift and this one's with the ethyl group shift. So when we move the methyl group onto our carbocation, this is the methyl group that jumped onto there. There's no stereocenter here. So that means that when the chlorine jumps on, we just add our chlorine and we have a happy molecule. And when the chlorine added onto it, it also did not form a stereocenter, which is why there's no wedges and dashes in the structure. We have a smiley face because we're all done, no extra work. However, when we move the ethyl group, the addition of this ethyl group onto the carbocation forms a stereocenter. So that means that we have two different carbocation molecule options. One of them where the ethyl group adds as a wedge, and the other one where one where the ethyl group adds as a wedge, and the other one where the ethyl group adds as a dash. So now we have two different options for when we add our chlorine. However, further, when we add our chlorine molecule, it also forms a stereocenter. So that means that this molecule can form again when the chlorine adds, so that the chlorine could either be a wedge right here or it could be a dash right here. And now we have to do it the opposite way. Our dash ethyl carbocation is either going to have the chlorine form as a wedge or form as a dash. And that means that we have 5 major products. This is 1, this is 2, this is 3, 4, and then the other one that we formed up here that was super easy, piece of cake. Okay, and we know that they're minor products, but we don't really have to worry about those, they're minor. So this is the entirety of just one big problem. It's kind of scary, but recognizing why you're doing what you're doing is what I think makes it a lot easier. So try it by yourself, see how you do, and just comment if you have any questions, and I'll be happy to help out. Hope this helps.